So this is exam 2. The first thing I just want to reiterate from class notes is that you need to draw a free body diagram for every application of Newton's second law or the moment equation. Okay. So that's just, it's an important tool that people use. It's a way to communicate with other people because you can't do a correct free body diagram without understanding how the loads from a joint work. And without understanding when you're doing structures, in order to do good free body diagrams, you have to understand the rules of structures. It really would be a plausible description in this class to say that the number one skill in this class is doing accurate free body diagrams. So you just have to do those. And related to that, this was one that came up a couple times. The reason that free body diagrams are useful is because they give you everything that you need for the left side of your of Newton's second law. So there were a couple of cases where people did free body diagrams with loads that were wrong, but then when they went to Newton's second law, it was right. You know, I mean, I was pretty lenient on that. I made notes if yours was that way on there. But the whole benefit of a free body diagram is that you're going from the free body diagram and writing that stuff directly into the table and then Newton's second law. So so those really should always match. There should never be loads in Newton's second law that aren't in the free body diagram or vice versa, you know. And if you take dynamics with me, these tables and everything are going to look exactly the same in dynamics that they are right now in statics. So these are skills that are going to transfer, excuse me, that are going to transfer into the future. So, okay. Anybody have any questions about exam 2? I'd be happy to go through parts of a problem or all of a problem or whatever. I guess, anybody? There is one thing that I wanted to say. So this was the one that that came up a couple times. It came up on numbers 1 and 2, but let me just do it for number 1. So you have a beam like this. And a roller. And a force like this. And so the free body diagram you have a weight force. I'll just put it up here to, no, I won't. Put it down here. It has a mass of 10 kilograms, so this is 98.1 newtons. And then you have the 500 Newton force. And then the roller, the rule is perpendicular to the surface, toward the chosen body, give it a name. That's a scalar variable, not a vector variable, so that shouldn't have a vector symbol over it. And then the pin joint should be an unknown force vector. And if you think about, you can think about these joints in terms of, so just go to each joint individually and think about what motions are allowed and what motions are not allowed. At the roller, if you get rid of everything else going on, this thing can move freely along the x-axis horizontally. So there can't be any force along the x-axis. It's not doing anything to prevent that motion. Perpendicular to that, yeah, it would be allowed to move up. But without absolute values, we can't specify up or down. So the key thing is it doesn't allow it to move down. And so yes, there is a force vertically. Okay. And then this could rotate without any restrictions. So there's no couple. And a few people put couples in their free body diagrams for this joint, and then in number 2 also. So if a joint allows rotation, if you take the other things away and that joint would allow rotation, you know there's no couple. Okay. All right, so that's about it for what I want to say about exam 2. Anybody have any homework questions you want me to go over? I could go over problems or answer questions. Otherwise, we're just going to sort of get into structures and spend some time working on structures, which I've said before is kind of the number 1 topic in this class. So it's nice to have some time to work on it. Okay, so structures. The most important topic in this class. And in the lecture video on structures, I gave you sort of a set of steps you could follow. I am going to just go through some example problems. Following those steps. Okay, so the first one. So let's say that we have a vertical wall and 2 hinges connected. And then 2 rigid members connected to each other on the upper right, in the upper right corner. And then at the midpoint of this one, we have a downward force of 300 newtons. At the pin, we have a force of 200 newtons. And it makes an angle of 10 degrees with the horizontal. And the length of the horizontal member is 0.75 meters. The length of the diagonal member is 1.25 meters. The horizontal one has a mass of 15 kilograms. The diagonal one has a mass of 25 kilograms. And we want to calculate let me put it like this. We want to calculate the external loads on each member. And the first thing that you're supposed to do in these structure problems is number the members. So I'm going to call this member 1 and this member 2. That's arbitrary. It doesn't, you could number them the other way, and in the end, you'd get the same answers. And now I'm just going to go through the rigid body analysis based on what we know about these types of joints for each one of these members. All of these 3 joints are pin joints, which means they just apply an unknown force vector to the body they're connected to. I'm going to start with a free body diagram. So this is for member 1. Okay, so what do we have here? Well, there's a weight force that acts at the midpoint. So 15 times 9.81 is 147.15 newtons. And then there's the given force of 300 newtons, also at the midpoint, just because that's where we're told it's applied. And now the rest take a little more thinking. So we have the 2 joints, and we have this 200 Newton force applied, okay? Let's first think about that 200 Newton force, okay? The most common mistake people make is to assume that a force like that that's applied at a joint is applied to every member connected to that joint, okay? But what that does essentially is that has the same effect as, like, if I applied that 200 Newton force to member 1 and then to member 2, that's like having this be a 400 Newton force, okay? For what it really does is you have to decide on one of these 2 members to receive that force. And in the video, what I said, I mean, you might as well use the bookkeeping method I use, I think, although there's no reason that you have to do it that way. But I always apply that force to the lowest numbered member of that joint, okay? You could do it for the highest numbered member. You could do it to the member that, you know, is the most green or whatever, you know. You just need a bookkeeping rule so you don't double count it. Okay, so the lowest numbered member at that joint, the joint being the pin joint in the upper right, is the one we're doing here. So I'm going to apply that 200 here. And when we get to the next body, I'm not going to put it on the other body. Okay? Any questions about that? And now, question? And now I'm going to deal with the joints. So over at the left, it's a pin joint. And I guess I'll name these joints. I'll call this joint A, B, C. So this is an unknown force vector since it's a pin joint, and I'll just call that reaction A. You could use the double subscript notation on this. This would be the force on member 1 by the wall or by the pin or something like that. But since we're never going, the benefit of that double subscript notation is that when you go to the other body, it makes Newton's third law really easy. We're never gonna isolate the wall, you know, and so this doesn't really have a benefit using the double subscript notation here. So I'm just going to call that RA. And now let's go over here. So this this force, it's a pin joint, so that's why we know this is an unknown force vector. And this is the force on body 1 by body 2. And now we've covered everything going on, so this is a complete free body diagram. Anybody have any questions about any parts of that? Yes?
What happens if, could we split it between 100 and 100 for each unit?
You could do that. In the end, it would give the same thing. It's then you have to do the math of dividing it in two and all that stuff. I would just put it on one and not the other. So now I'm going to go to the table. And we need to choose an about point, and it doesn't matter where you choose that. I'm going to put my about point over here. So I'll start with the force RA that is happening at the about point. The rho vector is the vector from the about point to the point where the force is applied. So in this case, that's 0. The force vector is RAX, RAY. Cross product is this times this minus this times this. And so that's just 0 here. And now I'll go to the 300. From the red circled about point to where that 300 is applied is positive 0.3750. The force is 0, negative 300. And so you get a moment of negative 112.5. These rho vectors have units of meters. The force vectors have units of newtons. So what are the units of the moment? Newton meters. Okay. So if you're in SI units, moments and couples are always in Newton meters. Also, are these moments vectors or scalars? I'm just writing them down as if they're scalars. They're vectors. So you have to remember that what we're doing here is leaving off, just to save space and time and whatever, I'm leaving off the z components of the rho and force vectors because we're in the plane. And that means that this is only a z component of the vector. The only non-zero component of the moment is z. Okay? So remember, those are really vectors, even though we're writing them as if it's just a number. Now I'll do the weight. It's happening at the same point, so that rho vector has to be the same. The force is 0, negative 147.15. And so the cross product is negative 55.18. And now I'll do the force F12. The rho vector is positive 0.750. The force is F12 X and Y components. Cross product is 0.75 F12Y. And last is the 200 Newton force. So the row vector is the same as it was for F12. The force vector is 200 times the cosine and sine of negative 10 degrees. That comes out to be 196.96 and negative 34.73. And so the cross product is negative 26.05. And we have a row for each one of the loads here. So we know we're done. 1, 2, 3, 4, 5 here, 5 rows, so we know we're done. And now I'll go to Newton's second law. We're just going to add up all of these forces in the force column and set it equal to 0. So we have RAX, RAY plus 0, negative 300, plus 0, negative 147.15, plus F12X, F12Y, plus 196.96, negative 34.73, those all add up to be 0. So those are our first two equations. Somebody asked me on the exam if I require that you write it out in this Newton's second law form. I don't require that. If you can put this into an equation form you like better from the table, right from the start, like I actually, when I'm doing these problems myself, I don't usually write this out. I just jump right to the part where I say the first equation is RAX plus F12X is equal to negative 196.96. And then the second equation says RAY plus F12Y is equal to 481.88. Okay, so I'll box those. We're going to have to come back and use those once we get a big system of equations. There's nothing we can do about it yet because you can see we have 4 variables and only 2 equations. And next I'll use rotational Newton's second law, the moment equation. I'm going to add all those up and set them equal to 0. So we have negative 112.5 minus 55.18 plus 0.75 F12Y minus 26.05 is equal to 0. And that gives us our third equation that says 0.75 F12Y is equal to 193.73. Okay, so right now we have 4 variables and 3 equations. If you wanted to, you can look at this and see that we can solve for f(1,2y) right now, reduce the number of variables by 1, reduce the number of equations by 1. You know, if you just want to make everything a little smaller, in the end, the system of equations you have to solve. But I wouldn't even bother with that. In the end, you're going to use reduced row echelon form to solve this big system. Might as well just keep that in there as an equation. I don't think it's really worth the time it takes to look for stuff like that. Okay, so I'm just going to leave that as a third equation, and then we'll just go on to the second body. All right, done with body 1. Any questions before we go on to the second one? So now we're going to do a free body diagram of body 2. And this is the diagonal one. We have a weight force acting down. That's 25 times 9.81, so that's 245.25. And now I'll think about the joint down in the lower left. That's a pin joint, so we know that's an unknown force vector. So I'll just put that in as RC. Again, we could write that as the force onto by the wall or something. Nothing wrong with that, but we're not going to ever isolate the wall, so it just doesn't really benefit us. And then we'll go up to the connection between bodies 1 and 2. That's a pin joint, so it's an unknown force vector. And it is the force onto by 1. And then this is an important step. If we left it like this, we would end up with a system of equations that's unsolvable. But Newton's third law says if 2 bodies are applying forces to each other and you switch which body you're looking at, it just switches the direction of the force. So instead of calling this F21, since we've already used the force vector F12, switching the subscripts is just multiplying it by -1. So we're just going to call this negative F12. Okay. Why would this be unsolvable if we left it as F21? Do you have a feel mathematically for why that is? That's right. Yeah, you just have, we'd just be adding 2 new variables. We'd have 8 total variables and only 6 equations. If we use this as negative F12, we still only have 6 variables and we can solve it. So you have to do this. And then what about that 200 Newton force? Well, with my bookkeeping rule that I follow, I only apply this to the lowest numbered member. Okay. And if you do that, follow that same rule, then it'll be easier to follow my examples and stuff. The benefit of using a different rule would be, it would be sort of funny to imagine me having to redo this problem every time I grade your exams because it doesn't match everyone else's. Okay, yeah, that's funny. Objectively, that would be funny. But I think it's better. It will be better for you in the long run if you just do what I do, you know. Okay, so row, force, moment. What do we want to use as an about point? I guess I'll use this. And notice that when you choose your about point, one way to think of what you're doing is you're just choosing that for that body as the origin, and then you're just finding the coordinates of all these other points. So I think maybe sometimes that's a helpful kind of way to think about it for people. Okay, so one thing that's going to make this easier is notice that this structure is a right triangle, and it's a 3, 4, 5 right triangle. So that makes this distance I guess that must be 1. Is that right? No, 1. Let's see. So 3 divided by 4. Yeah, 1. That doesn't make sense though, does it? 3, 4, 5. 3, 4, 5, 1. Yeah, okay. Okay, so the height is 1. The horizontal distance is 0.75, and we can use that to come up with these values. So I'll start with this force RC that's at my chosen about point. So the row vector is zeros. The force vector is RCX, RCY. Cross product is 0. Then the weight. I want to show you a little trick here, a little geometry trick. If you ever want the coordinates of the midpoint of 2 points, you can just average the coordinates of the two. So instead, I'm going to first go to this one. I'm going to come up with the coordinates or the row vector for this one. And then I know that since this is the midpoint between those two, the row vector for this is just going to be the average of the row vector for those two. Are you with me on that? No? Okay, I don't care. Okay, so I'm going to go to negative F12. The row vector for this is 0.75, 1. The force vector is negative F12x, negative F12y. And the cross product is negative 0.75 F12y plus F12x. Remember, this is just a z component, so those aren't two components of a vector. That's all added together to a single component. And now we're doing this force that's at the midpoint of those two. Well, what's the average of 0, 0, and 0.751? It's just 0.375.5. It's the average of each one of those components. So sometimes that's a nice little trick. The force is 0, negative 245.25. So we got 0.375 times negative 245.25. So this comes out to be a moment of negative 91.97. And we have 3 loads on the free body diagram, 3 rows in the table, so we know we're done. And now Newton's second law. This time I'm going to skip writing it out and I'm just going to put it into the equation form. So our fourth equation is going to be add up all the x components and set them equal to 0. So we have RCX minus F12x is equal to 0. Our fifth equation is the y components of Newton's second law. So RCY minus F12y minus 245 is equal to 0. But I'm going to get that constant over on the other side because we're going to be using reduced row echelon form eventually for this. So positive 245.25. And now we'll go to the moment equation. So equation 6 says negative 0.75 f12y plus f12x is equal to positive 91.97. Okay. All right, so we have 6 equations. Let's think about how many variables we have. Hopefully it's 6. So we have, if you look at these equations, we have RAX, RAY, that's 2. F12, X and Y, that's 4. And then RC, X and Y, that's 6. So our variables are RA, a full vector of those components. F12, a vector of those components. And then RC, a vector of those components. So we have 6 and 6, so it should work. And now I'm going to write out an augmented matrix for this. How many rows is this matrix going to have? 6. And how many columns is it going to have? Perfect. 7. Okay, so you also can do this in Excel. You can do it in MATLAB. I'm sure, I actually have never done this, but I'm sure you could just put it into ChatGPT, give them your equations, and it'd give you the answer. I really don't care how you solve these problems, the reduced row echelon form in your homework. But remember that you're going to have to do it with a calculator on exams. So be ready to do that. Okay, so let's see. Here are the 7 columns, and those are going to represent R AX, RAY, F12X, F12Y, RCX, RCY, and then the constants. And now I'll split this up into 6 rows, 1 row for each equation. So this represents equation 1, 2, 3, 4, 5, 6. Okay, so for equation 1, RAX plus F12X is equal to negative 196.16. So RAX, we have one of those. F12X, we have one of those. And the constant is negative 196.96. And everything I haven't filled in is a 0. Then equation 2, RAY plus F12Y is equal to positive 481.88. So we have a 1 here, a 1 here, and a 480, I already forgot, 481.88. Okay. For Newton's second law, a lot of times you'll see a lot of variables with this switched over one thing. That's just because one represents the x components and one equation represents the y components. And then for rotational Newton's second law, F12y's, we have 0.75, and then 193.73. 193.73. And like I mentioned before, if you want to, we could have gotten rid of this equation and already solved for F12y, but you don't have to do that. I just tend to carry all my equations and variables until the end and just let the algorithm give me the answers. Then equation 4, RCX's, we have 1. F12x's, we have -1. Then for equation 5, RCY's, we have 1. F12y's, we have -1. You can see that shifted over pattern again there. And for a constant, we have 245.25. And then equation 6, F12y's, we have -0.75. F12x, we have 1. Constant 91.97. And now it's just a matter of plugging it into the calculator and getting an answer. Anybody who has a calculator with you, will you punch this in? And so there's two things. One is practice doing this, and the other thing is checking my work. We'll just do this until 2 people have the same answer. Hopefully that'll happen on the first attempt. I'll write out what I get here. For RA, I got -482.66 and then 223.57. For F12, I got 285. Shut up while you're working on this, and I'll just write it down. Little wrinkle to understanding this. Like on a test, this would be the answer I'm looking for most of the time, and that would be the end of it. But interpreting this, I have to say one thing about this. If you chose your bodies to be the opposite, so if you chose your body 1 to be my body 2 and vice versa, okay, your numbers would not look like this once you got this answer, okay? And it wouldn't just be a Newton's third law thing. The magnitudes of those components would look different, okay? So even if, we both did it right, so what would it mean to get the same answers? What it would mean is once you calculated the final external loads on every body, those external loads would have to match. Okay, so let's redraw these in free body diagrams and I'll show you what I mean. Okay, so for body 1, over here we have RA, and that's -482 0.66 to 23.57. And then we have the weight force and the 300 Newton force. So 147.15. Those are at the same point, so you could add those together. And then the key thing over here is notice that that 200 Newton force and the force F12 act at the same spot. So we have to add those two force vectors together. Okay. I guess maybe I'll do it here just to be consistent. So this should be a downward 447. So this is going to be, so we have the vector 285.7, 258.31, and we're adding that to the vector 200 times the cosine and sine of negative 10 degrees. And so we get 482.66 to 23.58. And so notice both of those components look different than that F12. And all I'm doing is just, I'm going back to our original free body diagrams and just filling in the values that we calculated into the free body diagrams. And then any places where loads are happening at the same point, I'm adding those vectors up. Okay. And then now we'll go to this one. We have RC here. And at the midpoint, we just have the weight. So that's 245.25. And then up here, we included the 200 Newton force on body 1. It's not on body 2. So all we do here is put in negative F12. So this is going to be negative 285.7, negative 258.31. And once you go through those steps, no matter which body you chose as body 1 and body 2, these will match. Okay? You have to get the same external loads on each body. Okay? Let's do another one that seems similar, but there's one difference that this one has. So let's say that there is frozen. Okay, so here's the ground. And let's say that there is a pin joint over there. And it connects to a diagonal body and then it connects to a roller over here. And these don't look exactly the same length, but we're going to treat these like they're the same length. But then this time there is a third body that connects to these. And let's say that this angle is 30 degrees. This angle is 30 degrees. The length between these joints is 2 meters. And there is an external load here of 1,000 newtons. And I'm going to number these 1, 2, 3. And we're going to say mass of 1 and mass of 3 are both 10 kilograms. And mass of 2 is 15 kilograms. And we want to calculate the external loads on each member. Okay, so how many variables are we going to have in this problem? We have to have the same number of variables as we have equations. So you can answer that question by thinking about how many equations we're going to get.
9.
9, exactly. So if you're working in the plane, you have 2 Newton's second law equations for each body and 1 rotational Newton's second law equation for each body. So we have a total of 9. That means we're going to have 9 variables. That's a lot. And that's still a pretty simple structure, you know. When you're doing it on a hand calculator, once you get up into 12 and 15 and 21 variables and equations, it's pretty tedious to work with. It's not too hard to work with it though on a computer screen, or especially if this is a computer program that you're writing, you know. So we're just, even though this is kind of a tedious way to do this, the overall concepts here that you're learning are going to apply to much bigger things. Also, one of the next lecture videos you're going to see is going to be a simplification that you can use in some cases. Not in this case because we have masses, and I'll talk about why. But if we were able to assume that these masses were 0, we would be able to do this in 1, 2, 3, 4. I think just 5, maybe 6 equations and variables. And the bigger these systems get, the more benefit you get from this simplification. But we're going to learn this full method first because that simplified method only works in select cases. All right, so we have enough time. Let's break up. You can do it. You can do it in groups with the people around you, or you can do it by yourself. Compare answers after you're done. however, whatever you think is useful for you for trying to solidify this stuff. But let's just start with going to member 1. And the first thing we're going to do is take a couple minutes and come up with a free body diagram for member 1. Okay, so just take a couple minutes and draw out that free body diagram.
Can you scroll just a little bit so you can see it?
Yeah. All right, so member 1. So what do we have? Up at the, we have the weight at the midpoint, so that's 98.1. At the top, we're going to include that 1,000 Newton force in the lowest numbered member of that joint, which is 1. So I'm going to put that here. And then we have the force on 1 by 3. Okay. And now, this is something when you have joints that connect more than more than 2 objects. Okay, like up here at the top, we only connected members 1 and member 3. But the joint at the lower left connects members 1 and members 2, and also interacts with the ground. Okay, so what I'm going to do in that case is I'm going to say that the joint is part of the lowest numbered member. Okay, so one way to do that, one way to think about that is like, think of it from the side. And I'll label these. So let's call this joint A, B, and C. And so a side view of the joint at A, okay? And here's what it looks like. So we have member 1. So I'm sort of thinking of looking at it like this. That's me. Oh, look at my cute nose. Okay, so there's member 1 going up. Then member 2 going that way. This physically, you wouldn't make the joint this way, but this is just a way to kind of understand what's going on. And then so this is member 2. And then the third thing is the roller. And it's connected to the ground. And all of these are connected by a pin. Okay. So so what I'm going to do is I'm going to think of that pin and that roller as being part of member 1. So I'm going to, everything that's in green is what I'm going to think of as member 1. Shoot. Okay, that's all member 1. And now thinking about it this way can help you figure out what's touching what. Okay. So is the ground touching member 1? Yes. And so we use the rules for a roller over here. It's going to be, this force is going to be perpendicular to the surface, toward the chosen body, and I'll call that RA. Okay. Is member 2 touching member 1? Yes. And so there is a force on 1 by 2, and that's a pin joint connection. Okay. But notice that when we switch to body 2 and draw the free body diagram, if you look at that side view, the ground is not touching member 2. So that there's not going to be any reaction force RA acting on member 2. Okay. There is a section in the textbook document on D2L if you want to read a little bit more about that. There's a little, more elaborate, lengthy information about thinking about that. But this is a complete free body diagram now of member 1. Okay, so now take a couple minutes and write out the table for this and write out Newton's laws. Okay, so we're going to come up with the first 3 equations for our system of equations. Okay, so we have 1, 2, 3, 4, 5 loads to deal with. I'm going to put my about point down here at the lower left. And I'll start with RA. That's a scalar, not a vector. We know the direction of that. The row vector is 0. The force vector is 0 RA. Cross product is 0. And then I'll do F12. It's the same row vector of 0. The components are F12x, F12y. Cross product is 0. Then we'll go to, I'll go to the other end and then I'll use that midpoint thing. So I'm going to go to the 1000. The row vector is 1 and then 0.577. And the force vector is 0, negative 1000. And so the cross product is negative 1000. Then we have F13. The row vector is 1.577. The force vector is F13x, F13y. Cross product is F13y minus 0.577 F13x. And now the last one is the weight force. That's at the midpoint between 0, 0 and 1, 0.577. Bless you. So that is 0.5. And then 0.289. The force vector is 0, negative 98.1. So the cross product is negative 49.05. Yes?
Can I look at the diagram one more time?
Yeah.
Like where it says like 2 meters. So for the 1000 newtons, right?
Yeah.
For the x direction, that should be 1. Yeah, you got it. Okay, never mind.
Okay. Yep. Okay, so now I'm going to go, so I'll start with Newton's second law, x and y components. The first equation is the x component of Newton's second law. So that's F12x plus F13x is equal to 0. Now the y component of Newton's second law, we have RA plus F12y plus F13y is equal to positive 1098.1. And then last is the moment equation. I'll rearrange the two for the F13 row. So we have negative 0.577 F13x plus F13y is equal to positive 1049.05. Any questions about that? Okay, so now we're going to go to a free body diagram of number 2, the horizontal member. So let's start. I'll just give you a couple minutes to draw a free body diagram for that. Okay, so there's the body. And when we looked at that side view of A, we figured out that member 2 does not touch the ground. So we're not going to have any reaction from the ground. Member 2 does touch member 1, and it touches it through a pin joint. So there is going to be an unknown force vector on 2 by 1. And I'm going to reduce the number of variables by calling that negative force on 1 by 2. That's Newton's third law. And then we have the weight at the middle. So 15 kilograms times 9.81, that's 147.15. Okay, and now let's think about what's happening at this, at the joint C. Let's think about that from a side view. Okay, so side view of C. Okay. Well, we have member 3 going up and away if we're looking from the right side. So that's member 3. We have member 2 that's just going straight away. And then we have a bracket connected to the ground and a pin connecting all of these. Okay. Now I am going to connect the joint to the lowest numbered member at this that connects at this joint. So this time I'm going to consider that pin to be part of member 2. So all of this is member 2. Okay. So does the ground touch member 2? Yes, through a pin joint connection. Does member 3 touch member 2? Yes, through a pin joint connection. And so what we have here is the force on 2 by 3. And we also have, I guess I'll do it as 2 separate forces, the reaction at C. But notice when we isolate member 3, because that green, well, because 3 doesn't touch the ground in any way, those member 3 is not going to have a reaction RC on it. It's only going to connect to member 2. Okay. Well, this is a complete free body diagram. So now take a couple minutes and write out the table and the 3 equations that come from this. So I'm going to put my about point here. And I'll start out with negative f1, 2. The row vector is 0. If you didn't put your about point there, that's totally fine. Your equations will look different, but the solutions will all come out the same. Force is negative f1, 2 x, negative f1, 2 y. Cross product is 0. And then I'll do the weight force. So that row vector is 1, 0. The force is 0, negative 147.15. Cross product is negative 147.15. And then I'll go to F2, 3. The row vector is 2, 0. The force is F2, 3x, F2, 3y. Cross product is 2, F2, 3y. And then I'll go to RC. The row vector again is 2, 0. The force vector is RCX, RCY. Cross product is 2 RCY. We have 3 equations so far. So equation 4 comes from the x components of Newton's second law. So negative F1, 2x plus F2, 3x plus RCX is equal to 0. Then the y component of Newton's second law, negative F1, 2y plus F2, 3y plus RCY is equal to positive 147.15. And then rotational Newton's second law says 2F2, 3y plus 2RCY is equal to positive 147.15. Any questions about that? Okay, just so I can, so I have time to finish. Let me just go through body 3. Well, actually, we go to 12, don't we? I always think we go till 11:50. So why don't you take a couple minutes and do the free body diagram for member 3? Okay, so this is this body. At the upper left, remember that 1,000 Newton force acted on the lowest numbered member. It acted on member 1, so we don't want to include that here. So the only other force acting here is the force vector on 3 by 1, or negative F1, 3. Then we have the weight force at the middle, 98.1. And then at the lower right, that's the joint C. And if you look at C, the bracket for the ground is not connected. It's not touching member 3. So that doesn't go in here at all. The only thing touching member 3 is the pin, which is part of member 2. So now down here, we have the force on 3 by 2. And Newton's third law says that's negative F23. And so that's a complete free body diagram for member 3. Okay. So as a kind of general rule, the number of variables you have showing up in your free body diagrams decreases as the number goes up, because as the number goes up, you have fewer and fewer joints where that's the lowest numbered member. So you're touching fewer and fewer things. Okay, so now take a few minutes and write out the table and come up with your equations for this. Okay, so rho, force, moment. Oh, let me say one thing about, there's some solutions, if you're looking at structures solutions and rigid body solutions, that have 2 more columns in these tables. I don't teach it that way anymore. I used to say find the coordinates of where the force is applied, the coordinates of the about point, and then subtract them. That's what those two extra columns are that you see. So if you ever get confused about what that is, why those tables in some of those solutions are longer, it's just the coordinates where the force is applied and the coordinates of the about point. And then you can subtract those to get the rho vector. I think this is a nicer way to think about it, actually. It would be weird if I thought the other one was a nicer way to think about it and then I taught this way. That would be stupid. Okay, so that's going to be my about point. So first I'll do negative F23. The rho vector is 0. The force vector is negative F23x, negative F23y. Cross product is 0. Then I'll go up to the upper left. So negative F13. The rho vector is negative 1, positive 0.577. Force vector is negative F13x, negative F13y. Cross product is F13y plus 0.577 F13x. And then last is the weight. The rho vector is the midpoint of these two, so that's negative 0.5, positive 0.289. Force vector is 0, negative 98.1. Cross product is positive 49.05. We have 6 equations so far. So the 7th equation is the x components of Newton's second law. Negative F23x minus F13x is equal to 0. Then the y component of Newton's second law, negative F23y minus F13y is equal to positive 98.1. And then the 9th is the rotational Newton's second law. So I'll rearrange this, 0.577 F13x plus F13y is equal to negative 49.05. So that's 9 equations. And what are the variables? So hopefully we have 9 variables. Those are we have RC, that's a vector, so that's 2 variables. Then F12 is a vector. F13 is a vector. F23 is a vector. And then RA is a scalar because that's a known direction. So that's 2, 4, 6, 8, 9. And so we have a system of 9 variables, 9 equations, and we can solve it. Any questions about that? Let me just say a little bit about the truss simplification. So none of these example problems that we did today could use this really nice simplification called trusses. But sometimes you can, and it's something that's worth being aware of. So the truss simplification. It reduces the number of equations and the number of variables a lot. So it's pretty nice, but it only works when every member is a 2-force member. So a 2-force member means the only loads on a body are 2 force vectors. Okay, so what's special about 2-force members or 2-force bodies? So let's think about just a general body, and I'm purposefully making it a weird shape. Okay, and let's think of applying forces at this point and this point. Okay. And we're only considering these when they're in equilibrium. This is static, so everything is in equilibrium. But this isn't true. Stuff isn't true generally. It's only true if this body is in equilibrium. What would happen so let's say you have 2 forces, random forces like this. Those are the 2 force vectors acting on this body. Would this in general be in equilibrium? No, this would have some acceleration because those force vectors don't add up to 0, right? So for this body not to accelerate, so let's say for the acceleration to be equal to 0, those forces have to be equal and opposite. Okay, so already we know that if you have a two-force body, those two forces have to be equal and opposite. But let me give you, just an arbitrary set of equal and opposite forces. Let's say this and this. Those are supposed to be opposite directions. Would this be in equilibrium? No, because those two are a couple and they're going to make this thing rotate. Okay, there's going to be an angular acceleration from these two forces. So that doesn't work either. So how would you prevent that? In order for the angular acceleration to be equal to 0, those force vectors both have to be along a line between the 2 points. Another way to say that is that they have to have the same line of action. So there are only two possibilities for a two-force body that's in equilibrium. Okay, I'm going to... Come on now. So I'm going to copy this. No. No, I'm not. I'm just going to draw it again. Okay, so if you think of the line connecting those 2 points, the only possibilities are that these force vectors are away from each other along this line, or that they're towards each other along this line. Those are the only possibilities. And so the truss simplification exploits that, okay? So what's required for a structure to be made of two force bodies? The first thing is there can't be any weight. You have to be able to neglect the weight. And so for some applications, that's useful. For bridges and stuff, they'll make this simplification to get rough estimates pretty often because the weight of the bridge itself is small compared to the forces that these things have to support. So you have to be able to neglect the weight. And the second requirement is that all external loads have to be applied at the joints. If you can't make either of these two, if these two things aren't happening for a given structure, then that introduces third loads into these bodies. and it's not a two-force body, and you have to use the full approach that we're talking about right now. But if you have these, we'll get into in a separate lecture video how you can exploit that to reduce the number of equations and the number of variables. When in doubt, you can always use that full solution. It works for everything, the one that we're working on right now. Okay, that's all.